February 24, 1944, Anzio, Italy, night. On the night of February 24, 1944, two SCR-584 radar units were deployed hastily to Anzio and positioned in defensive emplacements, their structures sunk into the ground up to the roofs of their trailers. As darkness fell, 12 German bombers entered the area designated as beachhead airspace. By dawn, 7 of these aircraft had been eliminated, all by the precision of the SCR-584 directed 90mm anti-aircraft guns. This engagement left German intelligence baffled. 7 out of 12 bombers destroyed under conditions of complete darkness represented an extraordinary 58% success rate, far surpassing any previously known standards in anti-aircraft warfare. Prior to this event, even under ideal daytime conditions, anti-aircraft artillery typically achieved only a single kill per approximately 2,500 rounds fired. Surviving Luftwaffe crews described something entirely unprecedented: bursts of flak that seemed to anticipate their flight paths, detonations appearing precisely where their aircraft would be moments later, and a rate of fire that almost appeared predictive of their maneuvers. The remarkable effectiveness was not the result of individual skill or fortuitous targeting. Rather, it stemmed from the SCR-584, a groundbreaking microwave radar system capable of automatic target tracking. This innovation fundamentally transformed air defense operations, remaining largely invisible to German reconnaissance even as it systematically degraded Luftwaffe operational capacity. The German crews had unknowingly encountered the next stage of aerial warfare, a technological leap whose origins traced back to an earlier Allied scientific collaboration. The roots of this advantage lay in 1940, when British engineers shared the cavity magnetron with the United States via the highly classified TIZAD mission. This device, crucial for generating high-power microwaves, enabled the development of radar systems operating at significantly higher frequencies than anything the Germans were fielding at the time. While German radar development continued to rely on conventional meter-wave technologies, American scientists at MIT's Radiation Laboratory were working on a system that would redefine anti-aircraft strategy. The SCR-584 represented the pinnacle of this research. It could detect aircraft up to 40 miles away and determine their range with remarkable precision within approximately 75 feet. Operating in the 2700–2900 MHz band corresponding to wavelengths of roughly 10–11 cmates, the radar emitted 300 kW pulses lasting 0.8 microseconds at a pulse repetition rate of 1,770 pulses per second. German radar warning receivers designed to sense British systems operating between 200 and 600 MHz were completely unable to detect these signals. Beyond the disparity in frequencies, the SCR-584 introduced revolutionary automation. Using a conical scanning technique, the radar rotated its beam around a central axis, generating a cone-shaped detection pattern capable of locking onto moving targets and following them automatically without human adjustment. This combination of frequency stealth, range accuracy, and automated tracking created a technological edge that Luftwaffe forces could neither anticipate nor counter, reshaping the dynamics of nighttime air defense in the European theater. When paired with the Mi-9 gun director, an analog computer powered by 160 vacuum tubes, the system could generate firing solutions at a remarkable rate of 30 times per second. These calculations incorporated variables such as wind conditions, air density, the velocity of the target, and the effects of gravity on shell trajectory. Its first deployment at Anzio represented a pivotal turning point in anti-aircraft defense. For an entire week, enemy air attacks ceased. Only a lone plane dared to test the defenses and was immediately destroyed. Within the same week, an additional 10 units were installed, effectively neutralizing the Luftwaffe's threat over the Anzio beachhead. German bomber crews, accustomed to attacking Allied positions with impunity, suddenly confronted a defensive system unlike anything they had encountered before. The remarkable effectiveness of the system lay in its full automation. Once the SCR-584 radar operator locked onto a target and engaged automatic tracking, the radar maintained precise lock regardless of any evasive maneuvers. This tracking information was transmitted directly to the M9 director, which calculated the exact point in space where the shell and aircraft would intersect. Meanwhile, four 90mm guns mechanically linked to the director moved in perfect synchronization with the computed firing solution. German aviators described a puzzling phenomenon: anti-aircraft bursts that seemed to anticipate their every maneuver. When pilots executed a dive, shells detonated precisely where the aircraft would reach the bottom. When attempting to turn or evade, explosions appeared along their projected flight paths. This was not the familiar pattern of barrage fire. It was a level of accuracy achievable only through rapid mechanical computation far beyond human reaction times. Unlike the German approach, which relied on handcrafted radar sets built individually by skilled technicians in small workshops, the SCR-584 was mass-produced in American factories with automotive efficiency. Approximately 1,700 units were eventually manufactured to defend against enemy air assaults. Chrysler Corporation, the main producer, applied assembly line techniques that transformed radar construction from artisanal craft into an industrial-scale operation. By the end of August, 1,943 610 systems had been delivered. The Dodge Division produced unit number 1,470 by January 28, 1,944, with an additional 628 sets allocated to the U.S. Marine Corps, coastal defense units, and as spare components, bringing the total to nearly 3,000 systems. This output from a single company alone surpassed the entirety of German wartime radar production. The contrast highlighted fundamental differences in industrial philosophy. German radar systems, like the Würzburg models, required highly trained technicians for assembly, and each unit had subtle differences. In contrast, the SCR-584 relied on modular design and standardized parts, allowing soldiers with minimal training to perform rapid field repairs. Where Germany produced a few dozen sets, the United States manufactured thousands. During the D-Day invasion on June 6, 1,944 39 SCR-584 systems were deployed to counter Luftwaffe attacks on the landing beaches. These units were specially waterproofed for amphibious operations and provided an unprecedented protective envelope over the largest naval invasion fleet in history. One of the only two German pilots to reach the beaches, Joseph Priller, later recounted the experience. In post-war debriefings, he described anti-aircraft fire that was unlike anything encountered over 5 years of combat, highly targeted, precise, and forcing constant evasive maneuvers that made successful attacks nearly impossible. The Luftwaffe's failure was not a result of lack of skill or bravery, but of encountering a technology beyond comprehension. Survivors reported the same phenomenon observed at Anzio, fire that seemed almost preternatural, predicting their movements before they occurred. Furthermore, the SCR-584 proved decisive against Germany's vengeance weapons. Its ability to deliver calculated, automatic anti-aircraft fire demonstrated the transformative impact of mechanized computation in modern warfare, changing the dynamics of air defense and rendering traditional bombardment tactics ineffective. The Von-flying bombs, moving at speeds around 400 miles per hour along steady, low-altitude paths, would theoretically have been simple targets for anti-aircraft defenses. However, their velocity rendered traditional aiming techniques largely ineffective. To counter the threat, England deployed 20 SCR-584 radar units along the Channel coast, paired with 80 anti-aircraft guns equipped with newly developed proximity-fused shells. This combination dramatically increased the destruction of incoming Vons. On a remarkable Sunday, 97 out of 101 bombs were intercepted before reaching London, underscoring a transformative leap in defensive capability. During the first week of deployment, only 17% of Vons entering the coastal defensive belt were destroyed. By August 23, this figure climbed to 60%, and by the end of the month, 74% of all incoming flying bombs were neutralized. On an extraordinary single day, interception rates even reached 82%. The efficiency of ammunition also surged. Previously, 2,500 shells were required to down a single Von, whereas the new system reduced this to just 100 shells per bomb, a 25-fold improvement that signified a decisive turning point. For the first time, defensive technology had overtaken the offensive capability of the attackers. German observers stationed along the French coast were astonished to see bombs destroyed with precise bursts of merely 3 or 4 shells, defying all their prior assumptions about anti-aircraft warfare. This tactical surprise was rooted in a fundamental scientific misjudgment by German radar engineers. In January 1943, a team led by Professor Abraham Esau persuaded the German High Command that radar operating at centimeter wavelengths was physically unfeasible, arguing that such short waves would not return enough energy to be detectable. Consequently, Germany ceased all research into microwave radar. When British H-2's radar units were captured in February 1943 and revealed to operate on centimeter wavelengths, it was already too late. Germany had fallen irreparably behind in this critical technology. German intelligence consistently misread the growing evidence of Allied radar superiority. Reports from pilots describing seemingly impossible anti-aircraft accuracy were dismissed as results of enhanced training, superior optical sights, or simply a higher density of guns. The notion that the Americans had achieved automatic radar tracking using microwave frequencies remained inconceivable to the Germans until late 1944. Throughout that year, Luftwaffe electronic warfare units relied on outdated equipment. The Fu-227 Fensburg detector could only monitor frequencies between 170 and 220 MHz, while the Fu-350 NACS, though closer to the SCR-584's operating range at 2500–3750 MHz, still struggled to reliably detect it. More critically, German radar detectors were designed to identify search radars that swept briefly across targets, whereas the SCR-584 employed continuous conical scanning to maintain a lock on a single object. This fundamental difference rendered German equipment ineffective, leaving crews vulnerable as they unknowingly flew into highly accurate, radar-directed defenses. The SCR-584 system, developed by the Chrysler Corporation, combined multiple elements of advanced American engineering: a powerful radar unit, heavy 90mm anti-aircraft guns, an identification friend or foe (IFF) device invented by the British, a dedicated power supply, and an M9 gun director. Central to its capability was the cavity magnetron, which produced 300 kilowatts of microwave energy, exceeding the output of entire German radar networks. This integration of cutting-edge components enabled the Allies to intercept Von flying bombs with unprecedented precision, illustrating a clear technological dominance that Germany was unable to counter during the war. Analysis of production data during World War II exposes a fundamental imbalance in industrial capacity that ultimately determined Germany's fate regardless of battlefield ingenuity. In the United States, companies like Chrysler alone were able to manufacture nearly 3,000 radar units, with total confirmed output exceeding 1,700 units at a minimum. Additional contributions from firms such as General Electric and Westinghouse further augmented production. Economies of scale drove costs down from roughly $50,000 per unit to under $10,000, while peak monthly output surpassed 50 units. In stark contrast, German radar manufacturing, exemplified by the Würzburg system, remained limited and painstakingly slow. Total wartime production for all German radar types barely reached 4,000 units, each essentially crafted by hand. The Germans were unable to achieve meaningful cost reductions, and production capacity remained a constant bottleneck. This disparity reflected broader differences in industrial culture and organizational efficiency between the two nations. The American SCR-584 radar was explicitly engineered for rapid deployment and operation by conscripted personnel with only 6 weeks of training. German systems, in contrast, demanded highly trained engineers and technicians, often requiring months of specialized instruction. Beyond raw specifications, the SCR-584 offered practical benefits that multiplied its operational value. It could be fully operational within half an hour of setup, while German equivalents often required several hours. This agility proved decisive in fluid combat situations such as the Italian campaign, where radar units needed to provide immediate protection for advancing troops. Environmental resilience further distinguished the SCR-584. It maintained full functionality in rain, snow, and fog conditions that severely degraded German optical and radar performance. Maintenance was straightforward. Its modular design allowed operators to replace components with minimal technical expertise. German radars, by comparison, necessitated trained specialists even for minor repairs. Crew efficiency also favored the Americans, requiring only 3 operators versus the 8 needed for the Würzburg RIA. Post-war testimony from Field Marshal Albert Kessler highlighted the tactical impact. By early 1944, American radar-directed anti-aircraft fire rendered traditional German air support largely ineffective. Once a leader in integrated arms tactics, the Wehrmacht increasingly found itself blind to Allied movements, while Allied forces enjoyed comprehensive aerial observation. The campaign targeting the V-1 flying bombs offers measurable evidence of this technological edge. During the first week of operations, conventional interception techniques managed only a 17% success rate. By the 4th week, the SCR-584 enabled a 60% interception rate, which climbed to an average of 74% by week 8, with peak performance reaching 82% on the best day. Ammunition usage became dramatically more efficient, improving approximately 25 times over earlier efforts. These results marked the first instance in history in which defensive artillery consistently surpassed attacking aircraft in effectiveness. Despite the V-1's relatively predictable flight paths, its speed of roughly 400 mph had previously made it highly resistant to conventional anti-aircraft weapons. The SCR-584 fundamentally altered this equation. German electronic countermeasures, which had proved effective against British radar earlier in the conflict, failed entirely against the American system. Sophisticated jamming equipment designed for meter-wave frequencies could not disrupt microwave radar operation, and German chaff cut to similar wavelengths was equally ineffective. The failure stemmed not merely from technical shortcomings, but from an inability to counter a system that combined mobility, simplicity, and operational versatility with unprecedented industrial backing. During World War II, German electronic warfare doctrine operated under the assumption that their adversaries employed technologies comparable to their own. The notion that the Americans might rely on fundamentally different technological principles was largely ignored. It was only after captured American equipment was analyzed that the true capabilities of US OGs. Radar became clear, and by that point Germany lacked both the time and resources to develop effective countermeasures. One piece of technology, the SCR-584 radar, had consequences far beyond the destruction of enemy aircraft. By rendering German reconnaissance virtually impossible, it created a profound intelligence blackout for the Wehrmacht. Commanders were unable to monitor Allied troop movements, anticipate attacks, or identify vulnerable points in their defenses. This lack of reliable information was a significant factor in the strategic failures Germany suffered between 1944 and 1945. General Hasso von Manteuffel, who commanded the 5th Panzer Army during the Ardennes offensive, recounted the operational difficulties caused by this intelligence gap. "We advanced blindly in the Ardennes. Our reconnaissance aircraft could not survive over Allied positions. We had no knowledge of enemy reserves, no understanding of their maneuvers. Any hope for surprise, a cornerstone of our strategy, was impossible when visibility was one-sided." For Luftwaffe airmen, the SCR-584 represented a psychological as well as a tactical threat. This radar-directed anti-aircraft system removed the human element from combat. Experienced pilots, many decorated and battle-hardened, suddenly faced an adversary that relied on automated calculations rather than human skill. Survivors recalled the demoralizing effect. Headman Heinrich Baer, credited with 220 aerial victories, reflected, "Engaging enemy pilots was warfare as we understood it, skill pitted against skill, courage against courage." Radar-directed guns were not combat. They were execution dictated by mathematics. There was no honor in falling to a machine's computations. This shift, where human expertise became irrelevant, had a more profound impact on morale than fear of death itself. Luftwaffe pilots had long accepted the inherent risks of combat. What they could not tolerate was being reduced to passive elements in a process they could not influence. their years of training and experience rendered meaningless. After the war, Allied intelligence officers demonstrated the SCR-584 to captured Luftwaffe personnel. Responses varied from astonishment to reluctant acknowledgement. For many, the demonstration offered clarity and relief at finally understanding the nature of the threat they had faced. Dr. Wilhelm Runge, a German radar developer, later admitted in 1985, "We disregarded any reports that contradicted our assumptions about American capabilities. Rather than accept the truth, we devised intricate theories to explain away their precision. It was arrogance that cost thousands of lives." This institutional blindness was rooted in cultural assumptions within the Wehrmacht. Having been at the forefront of military innovation in the 1932nd, German commanders could not conceive that American engineers had surpassed their technological achievements. Even as evidence mounted in 1944, German leaders clung to the belief in their superiority. Following the war, the SCR-584 design influenced the development of U.S. Army missile systems, including the AMPQ-12 and AMPM-38, and the MGM-5 Corporal missile. Its core principles, automatic tracking, computer-assisted prediction, and integrated systems became foundational to all modern air defense. Today's surface-to-air missile systems can trace their conceptual lineage directly to the SCR-584, demonstrating the enduring importance of removing human reaction time from the targeting process. Despite wartime records being incomplete, available data highlights the SCR-584's effectiveness. At least 1,700 units were produced, with Chrysler alone contributing nearly 3,000 documented systems. Peak production exceeded 50 units per month. In combat, the system proved remarkably efficient. At Anzio, 7 of 12 bombers were destroyed on the first night, achieving a 58% kill rate. During V1 operations, interception success reached 82%, while ammunition use improved 25-fold compared to previous methods. On D-Day, 39 deployed units provided virtually comprehensive air defense coverage. The radar's detection range of 40 miles doubled that of contemporary German systems, and its accuracy, approximately 75 feet, vastly outperformed German estimates of 500 feet. Furthermore, automated tracking replaced laborious manual methods, and setup times decreased from over 2 hours to just 30 minutes. The German encounter with the SCR-584 illustrates enduring lessons about technological surprise. Confidence in one's assumptions, compounded by theoretical rigidity, led German leaders to commit aircrews against an unseen threat. As General Paul Deichmann noted, "We accepted what we wished to believe, and the evidence to the contrary was rationalized away." The achievement of American engineers, what our scientists deemed impossible, came as a shock. By the time reality struck, the Luftwaffe had ceased to function as an effective force. Ultimately, the failure was not in intelligence collection, but in the interpretation of that intelligence, a cautionary example of how underestimating technological innovation can decisively shape the course of conflict. German intelligence consistently noted the precision of American anti-aircraft defenses. However, these observations were largely ignored because they conflicted with prevailing assumptions about U.S. military capabilities. This refusal to acknowledge the evidence created a cognitive blind spot that proved far more damaging than any espionage or security leak could have been. At the heart of this technological advantage was the SCR-584 radar system, which exemplified American industrial strategy, mass production, standardized components, and simplified design. Rather than striving for individual perfection in each unit, American engineers prioritized systems that could be manufactured reliably and in great quantities. This philosophy, borrowed from automobile production, ultimately outperformed the German preference for meticulous, handcrafted precision in military equipment. The difference extended beyond engineering into operational doctrine. German forces prized specialized knowledge and technical mastery, expecting human skill to compensate for technological limitations. In contrast, American design deliberately minimized reliance on operator expertise, emphasizing automation and simplicity. The SCR-584's effectiveness lay in this approach. It could deliver high-precision results without demanding exceptional training or talent from its operators. This democratization of complex technology proved decisive in the all-encompassing context of total war. By the time the Luftwaffe encountered the SCR-584, the era of aerial combat as a duel of human skill was effectively over. Aircraft were no longer engaged by opposing pilots' courage or maneuvering. They were confronted by systems capable of calculating and striking with near-perfect accuracy. For German airmen, this represented a disorienting shift. Pilots who had entered the conflict as knights of the sky found themselves facing an impersonal, mathematical inevitability. Decades later, Johannes Steinhoff reflected on the profound impact of the radar. The SCR-584 didn't just destroy our planes.
It undermined our entire understanding of warfare. We believed battles were won through bravery, training, and initiative. The Americans demonstrated that victory increasingly depended on industrial capacity, technological innovation, and automated systems. Our skills as pilots were rendered secondary. The SCR-584 was transformative not because of the volume of aircraft it shot down, but because it symbolized the broader triumph of systematic technological advantage over conventional military virtues. German pilots confronted a weapon that neutralized human error in targeting. Despite repeated reports, their command dismissed accounts of seemingly impossible accuracy, labeling them as exaggeration. Evidence suggesting automatic tracking was ignored or considered unfeasible. By the time captured SCR-584 units were analyzed, the Luftwaffe's operational effectiveness had already been severely degraded. Acknowledging the true capability of American radar would have required German military leadership to confront fundamental deficiencies in science, industry, and military innovation, a psychological barrier they could not overcome. For Luftwaffe crews, each encounter with the SCR-584 represented a lethal engagement where outcomes were predetermined by machines. These pilots faced an invisible, automated battlefield where survival was calculated in advance, and no amount of personal courage could alter the result. In Europe's skies, the romantic notion of the warrior pilot gave way to a new reality, an era defined by automated systems capable of observing, calculating, and eliminating threats with a precision that humans could neither replicate nor anticipate. The SCR-584 exemplified this paradigm shift, marking a turning point in aerial warfare where industrialized technology, rather than individual heroism, dictated the course of battle. The influence of the SCR-584 radar extended far beyond its operational use during the war. It laid the groundwork for contemporary air defense strategies and demonstrated a fundamental truth of modern combat. The side that integrates automation into the targeting and engagement process holds a decisive advantage. The Luftwaffe experienced this reality firsthand as its forces were systematically dismantled, aircraft by aircraft, under the guidance of machines that operated tirelessly, with pinpoint accuracy and without hesitation. German pilots discovered, often too late, that they were not merely facing American soldiers with guns, but sophisticated systems of calculation radar networks that transformed the entire airspace into a controlled and lethal environment. In this new paradigm, the individual qualities of bravery, expertise, and experience became nearly meaningless against the cold precision of technology that could anticipate, calculate, and execute with relentless efficiency. This shift marked the emergence of a type of warfare where technological superiority, rather than personal valor, became the decisive factor in determining outcomes on the battlefield.